Nuclear fission is the force that powers nuclear bombs. It can also be used to generate massive amounts of clean power in the form of nuclear reactors. Nuclear fission was discovered December 17, 1938 by German chemist Otto Hahn. He is referred to as the father of nuclear chemistry. So what happens is when an extra neutron is added to an atom with enough force, it causes it to split into two. During the split, more neutrons are released, which continue on to split even more nuclei. This creates a chain reaction, and this chain reaction is called nuclear fission. Because uranium constantly undergoes spontaneous fission at a very slow rate, that is the reason that it emits radiation, and also why it's chosen for induced fission in power generation in nuclear plants. More specifically, 235, which is uranium-235 isotope atom, is used, and when it absorbs a slow-moving neutron, it splits into faster-moving and lighter elements. Elements such as krypton-92 and barium-141, which are the products of fission. It also releases 3 neutrons, which may fire off and hit other U-235 atoms. This is a chain reaction. Once started, it can keep going on to split more and more U-235 atoms. Each time the U-235 splits, it emits an incredible amount of heat, gamma radiation, and high-energy photon radiation. This process happens extremely quickly. Just to give you an idea of how efficient and useful nuclear fission is, a pound of enriched uranium, which is about 2 to 3% U-235, is equal to about 1 million gallons of gasoline when comparing power generation. The energy released from 1 kilogram of uranium is equal to the amount of energy released from the combustion of around 4 billion kilograms of coal. Enriched uranium pellets, which are 2.5 centimeters in length and have the same diameter of a dime, are attached to long rods, which are then collected together in bundles. These act as the fuel rods in nuclear reactors. These fuel rods are submerged in water in order to be cooled, or they would easily overheat and melt. The energy created from the fuel rods in the process of fission is emitted in the form of heat. This heat converts the water into steam, which drives the turbine above the reactor. The turbine then spins a generator, and the end result is electricity. The steam is then ran through a condenser, which converts it back into water, and the water is ran through the massive cooling towers that we've all seen. Those are the massive cement structures where you see the smoke or the steam billowing out. It soon passes through filters and runs back into the reactor core to be reused. Because of the massive amounts of energy being created by the process of fission, proper safety measures are required. If these are not properly followed, serious consequences and actions can happen.
The Chernobyl accident happened on April 26, 1986 in Ukraine. The Chernobyl power plant's reactor number 4 blew up after a cooling capability test, spewing 400 times as much radiation as the bomb dropped on Hiroshima. Unit 4 was scheduled to be shut down for maintenance on 25th of April, and a safety system test was planned to be carried out immediately before taking the unit out of service. The power level was brought down to 25% full power in order to perform the safety test, which was inadvisable because of instability, but not prohibited. On April 26, 1989, 2 distinct explosions were heard, the first being the initial steam explosion and the second most probably an explosion of hydrogen evolved in the course of zirconium steam reactions. Fuel, moderator materials, and probably some reactor structural material were rejected, and some, landing on the roofs of adjacent structures, starting a number of fires. Great East Japan earthquake of magnitude 9.0 at 2:46 p.m. on Friday, March 11, 2011, did considerable damage in the region, and the large tsunami it created caused very much more. The 15-meter tsunami disabled the power supply and cooling of 3 Fukushima reactors, causing a nuclear accident on March 11, 2011. All 3 cores largely melted in the first 3 days. 4 reactors were written off due to damage in the accident. After 2 weeks, reactors units 1, 2, and 3 were stable with water addition, and by July they were being cooled with recycled water from the new treatment plant. Official cool shutdown condition was announced in mid-December. Apart from cooling, the basic ongoing task was to prevent release of radioactive materials, particularly in contaminated water leaked from the 3 units. This was the largest disaster since the Chernobyl disaster in 1986. The 3 Mile Island Unit 2 reactor near Middletown, Pennsylvania partially melted down on March 28, 1979. This was the most serious accident in U.S. commercial nuclear power plant operating history. A combination of equipment malfunctions, design-related problems, and worker errors led to TMI-2's partial meltdown and very small off-site releases of radioactivity. The accident began about 4 a.m. when the plant experienced a failure in the secondary non-nuclear section of the plant. Either a mechanical or electrical failure prevented the main feed water pumps from sending water to the steam generators that remove heat from the reactor core. This caused the plant's turbine generator and then the reactor itself to automatically shut down. Immediately, the pressure in the primary system began to increase. In order to control that pressure, the pilot operator relief valve opened. The valve should have closed when the pressure fell to proper levels, but it became stuck open. Without the proper water flow, the nuclear fuel overheated to the point at which the zirconium cladding ruptured and the fuel pellets began to melt. By the evening of March 28th, the core appeared to be adequately cooled and reactor appeared to be stable.
In terms of prevention, these meltdowns, or formerly called nuclear reactor accidents, could have been prevented had there been no design deficiencies. Automation, which is a safe shutdown design feature in the case of external or internal electricity failures, hydrogen explosions, etc., etc. A proper understanding of the reactor's conditions and no human error. This goes for both Chernobyl and 3 Mile Island. At Chernobyl, however, reactor number 4 was being tested at a low loading setting to test whether power could continue to be generated after hours at the plant. This meltdown could have been prevented had the safety features not been disabled during the test, had there been no faulty process controls, no experimentation, and trust in automation by the Soviets. The plant was also built for military purposes and designed to operate at a plutonium production mode, so this didn't help. At 3 Mile Island, the meltdown could have been prevented had there been proper equipment and maintenance, no difficulty in using the emergency features, and no LOCA, so loss of coolant accident, which can also apply to Chernobyl. The Fukushima meltdown could have been prevented if there were no regulatory failures, meaning the elevation at which the emergency diesel generators were placed too low. One was actually located underground, and the others were located 10 to 13 meters above sea level. Potential tsunami heights were also underestimated during the design and building process, and this was after warnings from scientists about the height of the cliffs on which the plant was built. So those were ignored completely. There were also inadequate safety countermeasures, since all three safety systems failed. On a general scale, meltdowns can be prevented with proper design features, better maintenance of water flow in the reactors, sufficient plant design strategies and implementation of safety plans, automation, which is actually not present in 435 operating plants in the world today, better containment. Here we have an illustration of the containment structure, and this helps to prevent escape of radioactivity and to withstand high internal pressure. Prepared and highly trained operators can help prevent what can lead to a disaster. No fires, earthquakes, or loss of electricity as well, but of course the 3 remaining ones are not avoidable.
Hi, my name is Chris Winter, and after we talk about nuclear energy and the problems we've faced in the past, I'm going to talk about how we can improve for the future, which the major thing we can do is start researching integrated fast reactors, which we did have one in the United States which was started in the 1960s, known as EBR-2, which had 2 different safety tests, which it did pass with flying colors, which, according to the Nuclear Energy Division, the first test involved intentionally disabling the normal safety systems and cutting off all electricity to the pumps that drove coolant through the core, while the reactor is still at full power. The second test involved cutting electricity to the secondary pump so that there was nothing cooling the reactor, which would normally cause a meltdown in the current reactors. A nuclear engineer at this facility during these tests, named Pete Planchin, said that in both tests the temperature went up briefly and the passive system safety mechanics kicked in and began to cool naturally. Within 10 minutes, the temperature had stabilized near normal operating levels and the reactor had shut itself down without any intervention by human operators or emergency safety systems. Sadly, it was shut down in 1994 because it stopped receiving federal funds. You may be asking, why should we research this process? And IFR is able to use the normally non-fissile uranium-238, which would allow it to use nearly 100% of the uranium mined from underground, instead of the 1% that the current reactors are able to use. And IFR is also able to use the nuclear waste from the current reactors as fuel to create more electricity without even having to mine for more uranium, which the nuclear waste from these IFRs is only radioactive for a few hundred years, instead of the tens of thousands of years that the nuclear waste is radioactive from the current reactors. Another major reason why we need to convert to the from the current reactors to IFRs is that according to the World Nuclear Association, we only have enough uranium to last another 90 years. Another major thing is if we start using these reactors are able to use uranium from seawater, which, according to a professor emeritus of physics at Pittsburgh University known as Bernard Cohen, said that we have enough uranium in seawater to last us 5 billion years, which is longer than the expected life of our sun, which would cause uranium to be considered a renewable resource. Since it's a renewable resource, we would be able to most likely get rid of coal, which, if we're able to get rid of coal, we'd be saving approximately 1.9 pounds per kilowatt hour of CO2, which in Arizona alone, we use approximately 2,665,000 megawatt hours of electricity from coal, according to the U.S. Energy Information Administration, which this would equivalent to about 5 billion pounds or 41 billion cubic feet of carbon dioxide we are saving per year, which this would be enough carbon dioxide to fill Empire State Building over 1,000 times. Which these were just some of the many reasons why we should start researching this type of reactor.